Imagine for a second that you're trying to teach someone how to cook. Like you really want them to master the fundamentals of flavor and technique.
Right, the absolute basic.
Yes, exactly. But instead of giving them, a standardized, clearly printed culinary textbook, you hand them thousands of messy, handwritten family recipe cards.
Oh man, that sounds like a nightmare.
It gets worse. I
Yeah.
mean, we are talking conflicting measurements. Like one card says a pinch, another says a smidge. There are grease-stained pages, crossed-out ingredients, and these weird, highly specific personal notes about, like, Aunt Betty's oven running 20 degrees hot.
Well, if you did that, you wouldn't really be teaching them how to cook at all. I mean, they would spend, what, 80% of their time just trying to decipher the handwriting?
Exactly.
And trying to figure out who Aunt Betty is rather than actually learning how to bake the cake.
You would be teaching them the mess, basically. You'd be teaching them how to navigate this chaotic archive of human quirks. And, well, welcome to today's deep dive, because that exact scenario is what the tech industry is doing to artificial intelligence right now.
Yeah, it really is. It's wild when you frame it like that.
So today we are digging into this highly technical, really provocative research paper. It's titled No Accidental Software Agent, First Canonical Code for Human Code. And it's by Jepson Taylor of Never Human Research.
It's a fascinating read.
It is. And our mission today is to extract the most mind-bending insights from this research for you. We are going to explore why AI coding is on the verge of becoming up to 100 times cheaper and faster. And it's not by making the AI itself fundamentally smarter.
No, it's about radically changing the very substrate of what the AI actually learns from.
Right. So let's jump right in. The central premise of this paper kind of flips our entire approach to training models on its head. Right?
It completely does. Currently, frontier AI coding models are just burning massive amounts of money and compute power, learning what the author calls human code entropy.
Human code entropy. That's a great term.
Right, because instead of learning pure software behavior like how data moves or how logic is executed, the models are just memorizing the folklore. They are memorizing architectural fashion trends and the deeply chaotic folder structures of human programmers.
So let's ground this in reality for a second, because the scale of that human code entropy is just staggering.
Oh, it's massive.
The paper cites GitHub's Octoverse 2025 report, and it logged 395 million public repositories.
Which is just a crazy number to even conceptualize.
It is. That equates to roughly 230 new repositories being created every single minute. So this isn't some pristine, governed data set that AI is feeding on.
Not at all.
The author actually explicitly describes it as a survival archive.
Yeah, and think about what a survival archive actually looks like in practice. I mean, it's a historical record built by humans for humans under extreme deadline pressure.
Right, we just need to get it shipped.
Exactly. It contains valuable logic, sure, but that logic is completely entangled with accidental implementation details. You have hundreds of programming languages, duplicated frameworks, wildly inconsistent naming conventions.
And the continuous integration dialects.
Yes, which are basically just custom duct-taped scripts that teams use to deploy their code.
And it's hazardous, too. Like, to give you listening an idea of the actual risks here, the paper notes that GitGuardian found 28.65 million new hard-coded secrets leaked into public GitHub commits in 2025 alone.
Wait, 28 million?
Yeah, over 28 million passwords and API keys just out there. So when an AI trains on this raw data, it is absorbing all of that hazard. It's learning all the weak testing practices and all those bizarre dependency rituals.
And the financial penalty for forcing an AI to operate in that kind of environment is severe. The paper outlines this concept of a fourfold tax that an AI agent pays when dealing with this chaotic entropy.
A fourfold tax, meaning it pays for the mess 4 separate times.
Yeah, exactly. 4 separate times during the life cycle of a single task.
Okay, well, let's walk through a hypothetical bug fix to see how that tax is actually collected. So, say you ask an AI to fix a billing error in your app.
Well, the first tax hits during training. Long before you even ask the AI to fix the bug, the model had to spend billions of parameters just memorizing all the different contradictory ways humans randomly name their billing variables.
Right, because one guy calls it invoice and another calls it bill.
Exactly. And it has to memorize how they structure their financial folders across millions of repositories.
Okay, so that's tax 1. Then the second tax hits when you actually make the request, right?
Yeah.
Context gathering.
Right. The AI has to read through all your chaotic local folklore. It has to scan dozens of irrelevant files just to figure out where the actual billing logic lives in your specific project.
Which then triggers the third tax, the reasoning, and retry loops.
Yep. The AI attempts a fix, and maybe it guesses the wrong custom build command because your team uses some undocumented deployment script. So the build fails, and the AI has to try again. It just burns tokens mapping the territory.
And finally, the fourth tax falls on the human reviewer. They have to untangle this messy, unconstrained patch the AI just guessed at to see if it actually solved the billing error securely.
And the paper groups this massive waste of resources under a really phenomenal term, agent sprawl.
Agent sprawl, I love that.
Yeah, agent sprawl is a fundamental substrate failure. We are basically paying frontier model prices to have an AI act as a repository cartographer.
Wow, a cartographer, just drawing maps of our messy folders.
Right. It is wasting computational energy guessing whether your team puts the database schema in the libs folder or the sarcisse folder instead of just writing the logic you asked for.
It's basically like trying to teach an AI how to drive by forcing it to watch thousands of hours of dashcam footage of bad drivers.
Oh, exactly. Drivers who are arguing over directions, getting lost, missing their exits, and just running red lights.
Yeah, instead of just handing the AI a map and a rulebook.
Yeah.
So if human code is essentially this chaotic survival archive triggering incredibly expensive agent sprawl, the logical next step is figuring out how to build that map and rulebook. Like, how do we clean the substrate up so that AI can just focus on pure logic?
Well, the paper's proposed cure for this is something called agent-first canonical code.
Agent-first canonical code. Okay, unpack that for us.
So the theoretical spine of this solution relies on a mathematical concept the author calls quotienting software by behavior equivalence.
Okay, hold on. For anyone listening who doesn't have a background in discrete mathematics, we need to translate quotienting by behavior equivalence into plain English.
Fair enough. Think about building a user login system. Right now, there are thousands of ways to write it. You could use Python with FastAPI, Java with Spring, Node with Express.
Right, endless options.
Exactly. You could name your authentication files differently. You could place them in different directories. In raw human code, those are all distinct, messy data points.
Okay.
Quotienting by behavior equivalence means taking all those different human encodings that accomplish the exact same outcome and collapsing them into one single, governed, standardized representative, along with all the evidence that proves it actually works.
Ah, I see. So we are standardizing the raw code into this rigid substrate before we even train the AI or let it operate.
Exactly. The AI shouldn't be asked to learn every valid, chaotic implementation out there. It should just learn the canonical representative.
Makes total sense. So to create this perfectly predictable world for the AI, the paper lays out 6 hard properties of a canonical standard. And these aren't just suggestions, right?
No, they are absolute constraints. The first one is fixed language roles, meaning you no longer get to pick a programming language based on personal preference or whatever is currently fashionable.
Wow, so no more arguing over Rust versus Go.
Nope. The canonical profile assigns one supported lane for the backend, one for the product surface, one for data, and so on.
That alone eliminates countless hours of engineering debates.
Oh, absolutely. And the second property builds on that. It's enforced file grammar, meaning source paths, tests, and schemas live in mathematically predictable places. There are no local folder myths.
So no hiding the database config in a folder named after some weird inside joke.
Exactly. The AI knows exactly where everything is before it even looks. Then the third property is canonical naming. Vocabulary is strictly controlled and tied to stable rules like actor, resource, policy.
Got it. So a user is always a user. It's never a client in one file and a customer in another.
Right. Which leads to the fourth property, and this is where it gets highly restrictive for humans: strict generated boundaries.
Restrictive how?
Well, if a schema generates a client or a test fixture, human developers are absolutely forbidden from hand-editing those generated outputs.
Wait, absolutely forbidden. I mean, think about what happens today when a developer manually tweaks an auto-generated database schema because they are, rushing to meet a deadline.
It creates a ghost bug. And then the AI later tries to interact with that schema, assumes it follows the standard pattern, and completely fails. Ah, okay. So by locking that door with strict generated boundaries, the AI never has to guess if a human tampered with the foundation.
Exactly. Now, the fifth property requires standard proof commands. Every change an agent makes maps directly to known, standardized, continuous integration jobs and artifacts.
So the AI doesn't have to guess how to test the code. The test command is just universal.
You got it. And finally, the sixth property is governed repository policy. Security measures like branch protection, secrets management, and deployment permissions are all generated from one central policy object.
rather than being manually clicked together by some admin in a web interface somewhere.
Right. So when you apply all 6 of these constraints, you fundamentally change what an AI is interacting with.
It's a completely different world.
But standardizing the folder structure and naming conventions still leaves the AI writing a lot of repetitive logic, right? And this is where the paper introduces its most powerful mechanisms: behavior cells and semantic patch cells.
Okay, this is the mechanism that actually scales the efficiency. So let's define a behavior cell for the listener. Sure, a behavior cell is a named, versioned, proof-carrying software primitive. Instead of dealing in loose text files, the AI deals in these cells.
So going back to the login system we mentioned earlier.
Yeah, instead of the AI rewriting a custom login page and authentication flow from scratch every single time, it pulls a certified cell. Let's call it auth.oadc.
And that cell isn't just like a snippet of code. It comes entirely prepackaged with its own database schema, its own security negatives, and all its own proof obligations already baked in and verified.
Exactly. And when the AI needs to modify that cell, say you want to add a new requirement to the login flow, it doesn't just hack together a raw text diff like a human would.
Right.
It uses a semantic patch cell.
Yeah.
It applies an intentional patch like add field or rotate secret, which transforms the cell while maintaining all the mathematical proofs that the cell still functions securely.
Wow.
And the paper targets these cells to absorb 70 to 90% of routine product code.
Okay, I have to push back here on behalf of anyone listening who architects software for a living.
Go for it.
If 90% of the world's routine software is suddenly built from the exact same prepackaged cells, doesn't this enforce a massive, terrifying software monoculture? Like if the canonical auth.oedc cell has a fatal security flaw, wouldn't a hacker be able to compromise thousands of companies simultaneously? Isn't the messy diversity of human code actually, well, a defense mechanism?
It's a great question, and the paper actually anticipates this exact threat model. Canonical does not mean a single, unchecked implementation that the entire world just blindly trusts.
Oh, it doesn't.
No. For critical behavior cells, the framework requires a practice called N-version programming.
N-version programming, meaning multiple independent implementations operating simultaneously.
Yes. So you might have 3 entirely separate teams write the underlying logic for the authentication cell using completely different languages or paradigms.
Okay, that makes sense.
And at runtime, the system can run those different versions in parallel and cross-check their outputs. You combine that with adversarial security reviews, canary rollouts where changes are tested on a tiny fraction of users first, and strict rollback paths.
I see. So it's governed intentional diversity rather than just unconstrained drift.
Exactly. Relying on the random chance that 2 developers happen to write their login code differently isn't useful diversity, it's just noise. If you need diversity for security or compliance, it must be explicitly engineered and audited within that canonical framework.
Okay, so collapsing millions of chaotic repositories into behavior cells and semantic patches, I mean, it's a beautiful theory, but standardizing all of this represents a massive upfront investment.
Oh, massive.
Right. So how does this actually translate to the crazy cost and efficiency claims the paper is making? We really need to look at how they're doing the math here.
Yeah, the denominator the paper insists on using is critical here. The most important metric to evaluate an AI coding agent isn't lines of code written per second, and it isn't the raw token cost of the model either. I mean, a cheap model might generate 1,000 lines of code for a penny, but if a human engineer has to spend 3 hours reviewing it, finding the hallucinated variables, and fixing the security flaws, that code actually cost hundreds of dollars.
Exactly, which is why the decisive endpoint the author uses is the all-in cost per verified correct change. We are measuring what it actually costs to get a working, secure, tested feature completely deployed.
And that metric includes everything. The source tokens, the context gathering, the reasoning time, the failed tool loops we discussed earlier, the security provenance, and the human review.
So when you eliminate agent sprawl by moving to this canonical substrate, the economic gains predicted by the central hypothesis are just staggering. I mean, they project a 30 to 150x improvement in training token efficiency.
Yes, and for inference, which is the actual everyday operation of the AI pulling these cells and assembling them, they project a 10 to 50x lower cost per verified change.
10 to 50 times cheaper. To make this tangible, it sounds like we are moving software development from a messy artisan workshop to a highly governed, futuristic assembly line.
That is the perfect analogy. Right now, the AI is a robotic arm wandering aimlessly around that messy artisan workshop. It's tripping over extension cords, searching through disorganized drawers for a specific wrench, and guessing how a strange custom screw works.
That's the agent sprawl. It's burning energy just navigating the environment.
Exactly. But in this new canonical system, the robotic arm is bolted to the floor of a spotless factory. The exact standardized part just rolls down the conveyor belt directly to the arm, perfectly timed, with the installation instructions preloaded.
The agent just does the assembly.
Right. And the paper actually provides concrete experimental data to back up this assembly line efficiency.
Oh, they actually tested it.
Yeah, they conducted a preliminary experiment using a parameter-efficient training method called Couleret on a 14 billion parameter model, specifically the Quen 2.5 coder 14B. And they fed this model 64,088 canonically translated agentic coding trajectories.
Wow, okay. So they didn't just feed it static, finished code. They fed it over 64,000 examples of the actual process of an agent solving a problem, but strictly within this perfectly governed canonical format.
Exactly.
So did the AI learn the rules of the factory floor?
The results were remarkably clean. They saw smooth learning convergence, but the most stunning data point came during the evaluation phase.
What happened?
Across 711 evaluation checkpoints, where they were testing the model's ability to operate within the rules, they recorded exactly 0 forbidden language markers.
Wait, 0. Over 700 tests and the AI made absolutely 0 formatting errors.
0. It never once hallucinated a Python command inside a Java file or strayed from the strict naming conventions.
That's incredible because normally large language models drift, right? They get creative when you really don't want them to.
Exactly. But here, the AI perfectly adhered to the constraints of the assembly line. Now, the author is careful to note that this single pilot doesn't definitively prove that a 100 billion parameter model can instantly replace a trillion parameter model in all scenarios.
Sure. It's just a preliminary test.
But it definitively proves that canonical data is highly learnable. When you remove the chaotic human noise, the AI simply starts wasting processing power on accidental formatting.
So if we follow this assembly line logic to its absolute extreme, where the substrate is perfectly governed, the factory floor is spotless, and agents are pulling proof-carrying cells instantly, where does this train actually stop?
Well, the paper introduces 2 massive futuristic concepts for the endgame of this technology: minimum functional description length, or MFDL, and the no accident horizon.
Okay, let's unpack the mechanics of MFDL. What does that acronym actually represent in practice?
Minimum functional description length is the absolute shortest canonical behavior specification, plus its evidence bundle, plus the renderer needed to produce a working system.
It sounds dense.
It is, but it is not about playing code golf to write the shortest possible text file. It is about distilling a software request down to its absolute purest intent, totally devoid of any historical scaffolding.
So if I want to build an application that lets users upload photos and, I don't know, charges them a monthly subscription fee, I'm no longer dealing with files, folders, and routing logic.
Right.
I am simply declaring the intent. The MFDL is the bare minimum information required for the AI to instantly snap together the auth cell, the media cell, and the billing cell.
Exactly. Which brings us to the ultimate theoretical limit, the no accident horizon.
The no accident horizon.
This is the point where all accidental, unconstrained software representation just vanishes from the routine product development cycle. And the paper concludes that a mature canonical foundry operating at this horizon has a strongly defensible planning limit of about a 100x all-in cost reduction for verified changes.
100 times cost reduction completely changes the fundamental economics of the digital world. Like the barrier to creating complex software drops to near 0.
Completely. In this limit, the AI agent operates a tightly constrained machine. Human code, like the traditional text files we've spent decades obsessing over, is entirely abstracted away.
So no one is just typing out code.
Well, bespoke, handwritten code is reserved only for irreducible novelty. Like if you are inventing a brand new cryptographic algorithm or a totally novel physics engine for a video game, then you write code.
Right, because the cells don't exist for that yet.
Exactly. But for everything else, authentication, billing, databases, user workflows, you simply use cells.
For you listening, just think about what this means for the definition of software itself. The text files and folders are basically just historical scaffolding. Once we hit this no accident horizon, we won't be dealing with source code at all. We will just be dealing with pure intent and logic.
It totally redefines what we consider software to be. Software is no longer the text file. The text file is just a generated exhaust.
Generated exhaust, like the heat coming off an engine.
Yes, exactly. It's just exhaust from the true software, which is the behavioral graph and the mathematical proof obligations. The MFDL is the blueprint, and the code is just the brick that gets generated and thrown away when the building is done.
Bring this all together, the biggest takeaway for you, the listener, trying to navigate this whole AI revolution, is that the shortcut to the next massive leap isn't necessarily about building bigger data centers to churn through chaotic data.
Yeah.
It isn't just about throwing trillions more parameters at the models.
No, it's about changing the data substrate entirely. It is about eliminating the accidental software, all those millions of human quirks, arguments, and stylistic choices, so that the AI can focus purely on solving problems and assembling logic.
It's about quotienting out the noise.
Exactly.
But this leaves us with an incredibly provocative question to ponder. If routine software actually reaches this no-accident horizon, if 70 to 90% of all code is just instantly assembled from proof-carrying cells by AI agents who never make a formatting mistake, what happens to human engineers?
Yeah, it's a profound shift.
Do programmers stop writing code altogether and simply become software philosophers? Do we start typing out the recipes entirely and just become the people who dictate the menu and taste the dish? If human engineers are only dealing in minimum viable novelty, leaving the routine assembly to the agents, you have to wonder, what will your role be in a post-code world?